So, how's everything? Did you guys revise the first lecture? Yeah, I uploaded yesterday. The lecture notes, the recording on YouTube, and also I uploaded the verse homework, which is due by the end of this Friday. So, the homework is just a few questions on the concepts that we learned in the last lecture. We're going to solve some, another example that might also help you comprehend the whole thing. So let's start with let's revise what we did last time. So last time we started to get the relationship between a position of a particle and the velocity and the acceleration. So we had S, we had V, we had the acceleration. This is the three main components of any particle or any body that is moving. We need to know what is the position with respect to an origin, what is the velocity, what is the acceleration. And we found out that the velocity is the time rate of change of the position, and the acceleration is the time rate of change of the velocity. And we can write this as the second derivative of the position with respect to the time. We were able, from these two relationships, to find that the acceleration, ds, is equal to v dv. And this is the differential relationship between the three quantities, the position, the velocity, the acceleration. So you have to get to know the three of them. You have to know how to use each one of these. So then we start talking about the integral relationship between these three quantities. So we found out that we can, like, say that from this, I can say that the velocity dt is equal to ds, and from this one, I can say that dv, ds here, dv is equal to a dt. So basically I say that ds is equal to this multiplied by this, where dv is equal to a dt. So you have these called the differential form. And these differential forms can be converted to integral form. How? You just integrate both sides. Once you integrate both sides, this is going to be equal to s minus s node is going to be the integration of dt from t node to t. Same thing here, you are going to integrate both sides. The integration of ads from s node to s is going to be equal to half v squared minus v node squared. And then if you integrate this one, it's going to be v minus v node, the integration of a dt, t node to t. We spent the whole lecture last time to find out how we get these relationships, and then we start talking, this is only if the acceleration is variable. What if this acceleration is constant? If the acceleration is constant, I take it out of the integration, because any constant in the integration can be taken out, and I integrate just ds. All right, let's see how we can use this information to solve a problem. All right, so I'm giving you here an example. Is my handwriting small? Should I make it a little bit bigger? Guys in the back.
Yes.
You see this clearly? Good? Okay. I'm not sure if you guys watched the recording. Any comments to make the recording? I don't know. Is the voice clear? The board is clear? I believe if you have the notes in your hand and listening to the video, you can catch up with what I'm saying. But if you have any comment, maybe you email me or something. Okay? All right. So here, for this example that we're going to solve, it says that I have a body start from rest, and when I say start from rest, that means at time 0, the distance s, or the position s, was 0, and also the velocity was equal to 0. And this body has a velocity that can be described as a relation of time 3t squared minus 6t. And this is, since I have the velocity as function in time, and that's meter per second, this is v. This is called the instantaneous velocity, because this equation basically is going to give you the value of the velocity at any instant of time, like at 1 second, 2 seconds, 3 seconds. Go ahead.
So is that m at the end of the homework equation, that's supposed to be meters per second, or is that an entirely different variable?
Can you repeat that again? You are talking about the homework?
Yeah.
What about it?
At the end, there's an equation we're supposed to be using, but there's an m at the end. Is that part of meters per second, or is that a different variable in and of itself?
I don't know, like I don't remember it, but if like I give you an equation like this, and I put a unit at the end that is not part of the equation, that means that's a unit, meter per second. But if it's a variable inside, that means this variable, but I don't think I use m as a variable.
It's outside the equation by parentheses, correct now?
And so it wasn't an equation. Okay, I'm gonna double check it. But definitely I definitely describe what does m represent if I have it as part of the equation.
Okay.
Yeah, I'm gonna double check it and see. Alright, so I have this velocity as an instant velocity, and I'm asking you to determine number one, distance traveled. 2, average speed. 3, average velocity. Last time I told you what is the difference between all of these, so let's find out. Okay, so the thing is, since I have distance to travel and I have velocity, so here, velocity is the derivative of the this displacement or the position, but if you want to find the position after the velocity, you have to integrate. Here's the thing. If you have the position, you have to differentiate the position to get the velocity, and you have to differentiate the velocity to get the acceleration. But if you want to go backward, if you want to get the velocity out of the acceleration, you have to integrate. Yeah?
So that velocity you said was instantaneous, you know that, or that's given to us?
That's given. Like once you have it as a function of time, that means time is the instant. So that's called instantaneous velocity.
Okay.
So, here's the thing, S, V, A. So if you want to get V out of S, you differentiate with respect to time. And here you differentiate one more time with respect to time, right? But if you want to get the velocity out of the acceleration, you have to integrate the acceleration with respect to time, and you have to integrate the velocity with respect to time. Are we all on the same page? Okay. So since I give you the velocity and I want distance, so distance, that means it also related to the position, so I need to integrate this equation. So I'm gonna use this equation, this one. So S minus S node is gonna be the integration of V dt from T node to T. Alright, since it starts from rest, so definitely S node is 0, T node is 0. So S as a function of t is going to be equal to the integration from 0 to any time. And by the way, I'm asking for the distance to travel at t equal all this at t equal 3.5 seconds. So I can keep this t until I get the equation, and then I substitute with 3.5, or you can put 3.5 directly, but I'm going to keep it t for now. So let's integrate v, which is 3t squared minus 6t with respect to dt. Can you integrate this? 3t squared is going to be
16.
3t squared. We are not differentiating, we are integrating. t to the power 3. 6t is going to be minus what? 3 t squared, right? Okay. Because you are increasing the power and then divide over the new power, right? Okay, so this is the new function of s. So I have s is equal t. All right, so if you want to find the position s at t equals 3.5 seconds, what I'm going to do, I'm going to substitute 3.5 to the power 3 minus 3 multiplied to 3.5 to the power 2. Once you calculate all this, it's going to give you a position of 6.125 meter. So that means this body at t0 was at 0 distance, but after 3.5 seconds, this body was here at t equal 3.5 and cut distance of 6.125 meter. Is that what I'm asking for? Did I ask you about the position of the body at 3.5 seconds? No, I asked you what is the distance traveled. Can you guys tell me what is the difference between the position after 3.5 seconds and the distance to travel after 3.5 seconds?
That even if you went like in the negative direction, you'd still have a positive answer?
Yeah, I have to include all the distance traveled, either positive or negative. The thing is, what I looked at, I only looked at 3.5, but the thing is, since you have negative here, there's a chance that this body made some velocity in the negative direction. If this is positive, there's no way that this body could have made any distance in the negative direction. Let's find out. Well, let's substitute in V, or actually we have S here. Let's find what is the S value at t equal 1 second. Can you guys find out? This is the rule of S. So I'm gonna put 1 to the power 3 minus 3 multiplied by 1 to the power 2. Can you give me? Negative 2. So how about S at t equal 2 seconds? So I'm gonna have 2 to the power 3 minus 3, 2 to the power 2. So this is gonna be 8 minus 3 multiplied by 4. So 8 minus 12 is gonna give you a negative 4. That means here, by the way, S, this is S at 2.5, and we already got S at 3.5, which was 6.125. That means there's some negative movement that we need to include it in the distance to travel. But the thing is, how can I know, or how can I know when the body changes the direction? The thing is, this body somehow moved that way in the negative direction, maybe cut negative 2, negative 4, but I want to know at what time it changes the direction and goes back in the positive direction. So I need to find out that. So to find the point that it changes the direction, this is the point when the velocity, like let's say as I said last time, I'm here, and then the thing is I started from 0 here, and then I went with a negative velocity, this is the positive, and I kept slowing down until my velocity is 0, and then I went positive back again. That's what happened here. The body was here and kept going in a negative velocity while it's slowing down in the negative until it becomes 0, and then it goes up in the positive back. So if you want to find out, basically you have to plot the velocity versus time. This is time, and this is velocity. So at t equals 0, what was the velocity? Can you guys tell me?
0.
0. At t equal 1 second, what was the velocity? So 1 second, 3 minus 6 is gonna be negative 3, right? So the velocity at 1 second is equal to negative 3, so the body was here. And then at 2 seconds, 2 seconds is gonna be 3 multiplied by 4, 12, minus 6 multiplied by 2, 12, so you're gonna have 0 velocity. So that means your body went here at 2, where the velocity is 0, and then this is 2, and it start going up until 3.5. If you want to find the velocity at 3.5, so let's see, V at t equal 3.5, so it's going to be 3 multiplied by 3.5 squared minus 6 multiplied by 3.5. This is going to be 15.57. second. This is the velocity, 15.57. This is how the velocity look like. Goes negative, negative, and then goes up, and then 0, and then goes up. And that's what happened with the spike. It went that way, and then goes 0, and then increasing back to the positive. So it had to do some part of the negative going down, and some part of the negative going up, until it came back to the positive again. All right, let's get back to this. How can I find the distance to travel? I need to find all the distance that traveled in the negative direction. So at t equal 2 seconds, this body cut -4, and then did another -4 to come back here, and then get back here at 6.125. So if you want to find the ST, so it's going to be -4 minus another 4, but all of them are plus, because I don't care about the direction, I care about the magnitude, plus 6.125. So this is going to be 14.125 meters. That is the total distance traveled. Let's find the average velocity. If you guys recall, the average velocity is V average is going to be the S final minus the S known over the total time. I only care about the initial position, 0. I don't care about the negative. I don't care about how much back and forth went. If you came back to the original position again, so your average velocity is 0. Because you went here, and you came back here, so you did positive and negative, they slash each other here. Because that is, it's called the average velocity, not the average speed. So I know that my body final position after 3.5 seconds was 6.125. Initial position was 0, the total time was 3.5 seconds. That is gonna give you an average speed of, average velocity of 1.75 meter per second. If you wanna find the average speed, that's completely different. Average speed, I care about every distance that you cut, either in the positive, either in the negative, like all of them. So I have to get the S traveled and divide it over the total time. The S traveled, we just got it, 14.125, and total time 3.5 seconds. And this is gonna give us 4.035 meter per second. All right, does anybody have any questions so far? Yeah.
If like, instead of it turning around at 2, what if it turned around at a decimal point? That, like, how would you find that number?
You have to go to this equation. Can you see this one? If you want to find the time that the velocity changed its direction, go here and put this equation equal to 0, and solve this equation. So for example, this equation, when I put it equal to 0, 3t squared minus 6t equal to 0. I'm going to take t, and then you're going to end up having 3t minus 6 equal to 0. So we're going to have two solutions. One of them is t equal to 0, and one of them is t equal to 6 over 2 is going to be 2. This one makes sense because the body starts at the initial point, t equals 0. That's the one that I'm interested in, at t equal 2 seconds. Because the velocity was 0 here, and then it changed its direction, like to go in the other direction. This is where the buoyant exchanges the direction. Okay? Yeah.
When you were calculating the position at the different times at t equals 1, t equals 2, for t equals 2, you have that the position is -4. So my question is, on the graph, why is coordinate 2 at the origin instead of -4?
This is displacement. This graph is velocity. Okay? So this is v, and it tells you where the v. So the position of the body was at -4, but the velocity at that time was 0 here. But at 1 second here, at -2, the velocity of the body was -3. So if you want to find the position, you have to plot this curve, t cubed minus 3t squared. So you can plot this curve, the same thing that we plotted this one. You're going to make another one like this. So you're going to find out at 0 is equal to 0. Let's find out at s equal 1 second. It's going to be -2. It's going to be something like this, and then -4, and then you are going to come back here at a specific time. So you're going to have a curve like this, and then you're going to have something like this.
Oh, okay.
All right? So here s, and here is time, and here is 1 second, here's 2 second, and 2 second was -4. At 1 second was -2, and then you came back here at what, how many seconds? Oh, alright, so it was -4 at 2, so we were right, and then at t equal, you need to find out where it becomes, s becomes 0 again. Here, so I didn't find it, I only cared about what is the final s at 3.5 seconds, alright?
Excuse me, how did you get the 15.57 meters per second?
I substituted with the velocity, in the velocity equation that I gave to you here, that is given, at the time that we are looking at 3.5 seconds.
Yeah.
So you basically 3 multiplied by 3.5 to the power 2 minus 6 multiplied by 3.5, you're gonna get the total velocity, just direct substitution. If you have v equal to 60, so v at 1 second is gonna be 1 multiplied by 6, at 2 seconds, 3 multiplied by 6. But this is a simple equation. If it's two-term equation, you have to substitute with the time at each term, okay? All right, so with this, okay. There's something, I'm not gonna spend much time on it, I'm gonna solve maybe a problem. It's called erratic motion. Erratic motion is like when you have your motion doesn't follow one curve, follow multiple curves. So let's put it that way. Chapter 12.3. Erratic motion. So the erratic motion, let's look, for example, at one of these velocities. Like, let's say v with respect to t. So, let's say you have a body is moving with a velocity that is increasing, like on a curve like this. However, at a specific point, at a specific time, t, let's say 3 seconds, it is changing the way that the velocity is. That is called erratic motion, when it doesn't follow the same curve all over the motion. Okay? So here, your curve is like going up, and then your velocity is constant. So that's if it's a composition of two motions. So this is actually how we define it. When a particle has erratic or a changing motion, that means its position, velocity, or acceleration cannot be described by a single continuous mathematical function. Like one function is not enough, like not the same like what we have here. The velocity can be described in one function, but if it's described by two functions, I can see this is kind of like a parabolic curve, y or v equal to t squared. But this one, v is equal constant, so that's two completely different functions. That's called erratic motion. This can be applied also for the acceleration and the position. So sometimes you can have the acceleration as a function of t. Let's say your acceleration is going up, and then your acceleration is going down, something like that. Let's say acceleration versus displacement. Sometimes you would have maybe, let's say, your acceleration is something like this, and then constant something like this. If there is an abrupt change in your function like this, two lines or two curves, that is called erratic motion. You need two functions to describe this motion. However, we can benefit from these things. If you guys remember the area under the curve, do you remember? Which is the definition of the integration? Like, if you take one strip like this, and this is actually our integration, like this is dt, and the value here is called v. So v dt, that is the area of this strip. If you integrate this from t equal to 0 up to t final, 0 to t, that is going to give you the area under this curve. And the area under this curve is going to give you s minus s node. It's going to give you s. So basically you can benefit if you have the area of all this curve, so you can get the position. Same thing here. If you integrate this, this is dt, and this is a. If you integrate a, dt is going to give you the area under the curve, and this usually gives you the velocity. Same thing here, if you get this one, but when you do this integration, you have to separate the integration because you have two functions. So you have one here and one here, so you're gonna have two integration with two different functions. Let's say that this is dt, and this is not dt, this is ds, because I have s here. And this is a. If you guys remember, the integration of a ds is equal to the integration of the dv. All right, so let's see how problems with erratic motion looks like. Example 12 wind. This example is from the textbook, Kepler textbook. If you want to go check, there's lots of solved examples there, and also there's unsolved examples if you want to solve more problems. Okay, so here it says that there's a biker is on a road, and the relationship between the time and the distance can be described by two functions. One of them is a parabolic, and one of them is linear. This function is s equal to t squared, and this one is s equal to 20t minus 100. Okay? Alright, and I'm asking you, since you already have s versus t, I'm asking you to construct the vt curve and the at curve. I want you to find the relationship between the velocity and the time and the acceleration and the time. But before I do this, I want to test you on your engineering sense. This is a second degree parabola, right? What do you think about the velocity? What degree is going to be? This is second degree. The velocity, you have to differentiate s, ds, dt. It's going to be what degree? Verse, right? It's going to be line. How about the acceleration? It's going to be constant. Because when you differentiate verse degree, you're going to end up with a constant. How about this line? When you plot the v, this is a verse degree. The v is going to be constant. How about the acceleration? 0, right? We solved the problem. Let's find out. But the thing is, if we...
Is that 20 or?
This is 20t minus 100. All right.
Minus what?
This is 20, t minus 100. Okay. So, since I have two functions, so I have to divide my problems or my solutions into two pieces. So the first piece, I'm gonna say, I need to know what is the time boundaries for this thing. Here I'm saying this curve is stopped at 10 seconds, and this curve is stopped at 30 seconds. So I can see a time from 0, more than 0, and less than 10. So I'm gonna deal with function s is equal to t squared. So if I wanna find the velocity, v is gonna be equal to 2t. Why? Because I have to do ds, dt, and this is equal to 2t. And the acceleration is gonna be equal to dv, dt, and it's gonna be equal to 2. I'm gonna do the same thing with the time from 10 to 30. I know that s is equal to 20t minus 100. So this is gonna give me velocity ds dt equal to 20. And the acceleration is gonna be equal to dv dt equal to 0. That's what we did a minute ago. So let's plot these two curves. Time, velocity, time, acceleration. And this is the boundary. This is the other one. That's what we did. We said that this is gonna be t squared, so basically I know that this is gonna be line. And this is line, so this is gonna be constant. So let's find out what is actually the value of the velocity. You can use either two functions. So at time t equal to 10 seconds, you can come here, v is equal to 2t, 2 multiplied by 10 is gonna equal you 20 meter per second. So I find what is this value, and it's gonna be constant until like 30 seconds. So that's how the velocity look like. You can actually substitute here. V is equal to 20. That is the constant that we have, all right? So either, because this point is at the two curves, so the value from this curve should be equal to the value from the other curve. How about the acceleration? The acceleration is constant, it's equal to 2 until 2 seconds, and then it's gonna be equal to 0 here. So this is 0, and this is 2. And that's how we get the V versus T and also a T relationship. Do you guys have any question? We solve it but visually before even we do all that. Yeah.
So it gets to 0 at 10 seconds or 2 seconds?
This is 10 seconds. Yeah. Because this all one line. 10 seconds, and then all the acceleration is 0 until 30 seconds.
Okay.
The end of the motion. All right. So right now we are done with the linear kinematics. So linear kinematics, that means that our body is moving on a line, and it's only one dimension. Like a car is moving on the road, just as moving here. What if my body is moving on the plane? Like let's say my origin is here, and some of you keep walking in the room, and in the XY, and I want to find the velocity and the acceleration and the position. This is a completely different game. So once you move on a line, that's a symbol. If you move on a plane, so when we move on the line, we have one line. This is a curve. Like let's say, yeah, this line, this, and it's 1x, and I'm just looking at just one dimension. But if you are moving on a plane like this, making motion that way and motion that way, or having a car, and this car is not moving in a straight line, it's like moving like this. So that's when we need to find different ways to measure the displacement, measure the velocity, and also the acceleration, okay? So right now we are gonna talk about curvilinear motion. General curvilinear motion. Let's say, since we are talking curvilinear, so that means that the body's moving on a curve. So let's say that we have this curve. And the thing is, since our body's moving on a curve, we need to have an origin to measure the position to. So let's say that the origin is the center of this curve. Your body starts here as an initial position and came here as a final position. So this is the origin. And right now we are going to describe the position not with S, we're going to describe the position with R. All right? So this is the initial position, and this is the final position. This is going to call it R dash. All right? And the difference between the positions is called delta R. You guys remember vectors? So this is what is all the vector quantity is all about. Like let's say that you have a point here, and let's say that this is xy. All right, and this is your origin, and your body's here. The thing is, you can describe the distance between this point and this point with a vector. It's called R vector. You either have to find the quantity of this vector and the angle, theta, and basically you put them like this, R as a quantity and an angle theta like this, because that's how I know where is this point with respect to this point. You need to tell me what is the absolute distance, and this absolute distance at what angle from the x-axis. That's a one way to describe it. And there's another way to describe it. You can tell me how much x should I move and how much y should I move. And this direction is called I hat, and this direction is called j hat. And then you have to tell me what is the x in the I hat, what is the y in the j hat. All right, so that is the vector quantities. So that's what all these delta are about. By the way, let's say I'm moving from this position to a position over there. When we want to find the differential position, I only care about the shortest distance. I don't care about that you moved on a curve like this or moved all the way to the room and came back to the position. That's called distance traveled. But the thing is, when we try to find out the position from this point to this point, it doesn't matter if you go that way on a curve, or that way, or that way, or that way. At the end of the day, you move from this position to this position. You need to find the coordinate of this. Let's say it's a 10, 6, and this is 0 and 0. Basically, you cut 10 in the x and 6 in the y. That is the position. This thing is gonna take us back to delta s. That is the s, the track. Imagine like this curved line, you straighten it up and you walked on it. So that is, if you did this, so that means you are still in the linear mode. But we are interested in both, the distance traveled and also the position delta r. So let's come back here. Position, we're gonna talk about the same quantities. Position, displacement, and distance traveled.
Is this still part of chapter 12?
Hmm?
Is that still part of chapter 12?
Yeah, we are still in chapter 12 for another, I don't know, couple weeks.
Okay.
All right, so the position, as I said, it's our vector. If you want to describe what is the position of any point, that is the vector that is going to tell me what is this position is. And the r vector, as I said, it should have a magnitude and direction. By the way, this displacement can be 2D or 3D, but we are interested only right now in 2D. If you want to find the displacement of this pin in the space, that's going to be 3D because you have to find x, y, and z of this pen. All right, so let's focus only on the 2D. The displacement is the delta r, which is the final position minus the initial position. This one minus this one is going to give you this one. And the distance to travel is the delta s, which is, it's not vector, it is a distance, which is the curved distance here, from this point to this point. You have to find all this distance. That is called the distance to travel. All right, how about the velocity? We are having an instantaneous velocity average velocity, average speed, and instantaneous speed. What is all that? An instantaneous velocity is very simple. It is the time rate of a change of the position. If your position is r, so if you want to find v as a vector, it's going to be dr dt. That is very, very direct. Average velocity, same thing. If you want to find the average, v average, so it's going to be equal to the final position r minus the initial position r over delta t. You want to find this, the final minus the initial, and divide them by delta t, which we call this delta r over dt, this position. So average velocity is interested in the distance to travel. Not, sorry, the differentiate, the different in the position. But if you are interested in the speed, so you have to look at the base that you cut the distance on, the S. So if you want a V speed, SP, so this is gonna be equal to delta S over delta T. You wanna find this delta S. But the thing is, let's say that you are moving on delta S with a rate, like you have S's changing over time. If I told you that S is equal to something 5t plus 6, so that means that your distance on this track is changing with this time. So there is a time rate of change on the track, and there is time rate of change of delta R. Okay? So if you want to find the V in instant of the speed, okay, so this is average, and let's say this is speed. So this is going to be equal to ds dt. Since I want an instantaneous speed, so I have to differentiate the distance. Here, I differentiated the position. What is the difference between the position and the distance? Here you are here you are here, like if you reach at that point. So, and it's different, all the time is different. Okay, how about the acceleration? The acceleration has two quantities. One is the instantaneous acceleration. The second is the average acceleration. So let's see what is the difference between them. The instantaneous acceleration is very direct, so it's A is going to be dv dt. And the A average definitely is going to be the subtraction of two velocities. You can say it is the velocity at the final position minus the velocity at the initial position divided by the time delta t, which is delta v over delta t. This one, which is the v average. Same thing like the linear one, we can write like this as like r vector and v vector and a vector, and the v vector is the r dot, that means it's the derivative of the position, and here this is equal to v dot, which is the derivative of the velocity, or it's equal to r dot, which is the second derivative of the position. You guys have any questions? This is most of the rules that we need for this part of this sub-chapter.
Why do you write the averages BSB instead of S?
You can write it whatever you want, just like this is how we agreed upon it, like,
Okay.
we say V speed, you can write V speed or VS. We just want to make it to distinguish between the average velocity and the average speed. All right, so the thing is, talking about the position in a 2D setting, there's different ways that we can describe the position in the 2D. The thing is, there's different coordinate systems. Can you guys name some 2D coordinate systems that you are familiar with?
Polar coordinates?
Polar coordinates. What are the variables in the polar coordinates? R and theta, right? So in a polar coordinates, you need to know, because it's kind of radial, so you need to know what is the R and how much theta that you have. What other coordinates that we have? We have x, y, the Cartesian one, x and y, so that's the most simple one. So let's find what coordinate system that we deal with when it comes to curvilinear motion. So you have coordinates systems. I have one, it's called Cartesian, which is x and y. And I have another one, it's called tangent normal, I'm gonna tell you about it. Not sure if you guys, have you heard about it before? Have you dealt in math problems that has tangent normal coordinate system? Okay, we're gonna talk about it. The tangent normal has T and N as the directions. 3 is the polar coordinate system, which we call it cylindrical or polar coordinate system, which is R and theta. We use each one of these depends on the type of problem that we have. Like if you have a gravitational acceleration, like let's say a body that is moving under gravity, so that gravity we know it's in the y direction. So usually we use this one. If you have a body is moving along a path, a curve that I gave it to you already, so we use tangent normal. If you have a body or an arm, usually in the mechanical system, it's all about arms. It's attached, like you have something like this, an arm, and this arm is hinged here, and this arm is moving. You know that this arm is moving with an R and theta. So we usually use R theta coordinate system. So let's just start with the XY coordinate system and see how we can solve a problem that has a movement in X and Y direction. All our movement, right, like before, was only in one direction. So this is example 12.9 in the Kepler textbook. So in the Kepler textbook, it says that at any instant, the horizontal position of the weather balloon, let's say I have X and Y. Since I said X and Y, that means that's the motion is in 2 directions. We were talking about a motion in this plane, but right now our motion is in this plane, okay? All right, so you have this balloon is moving that way, and let's say our balloon is something like this. This is called a weather balloon. So it says at any instant, the horizontal position of the weather balloon in this figure is defined by x equal to 8t feet. So the x position is equal to 8t, and this is in feet. Where t is the time in seconds, if the equation of the path, this is the path of the balloon. So the equation sounds like it's parabolic equation, y equal to x squared over 10. And this is in feet. All right? So you have the x position in terms of time, but you have the y position in terms of x. The thing is, I want to know all the position as respect to the time, because at the end of the day, I want my position r vector in I hat plus something in j hat, right? So I know my x position is 8t, right? How about my y position? How can I get it as a function of t? Yeah.
Divide x by 8.
And then what? You're gonna find t. If you divide x by t, I wanna find the position y, because the thing is here, r is x and y, right? So I have already x as a function of t, but y I don't have as a function of t, I have a function of x. Yes.
Can you use substitution?
Substitution of what and what?
X into y?
Yeah, I substitute this here. So basically you're gonna get y equal to 8t all squared over 10. So this is gonna end up with 64 t squared over 10 is gonna be 6.4 t squared, right? That is how you can get it. So I can get this here as 8t and this here as 6.4 t squared. So right now I have the position in the x direction, in the y direction. So I have the position and time. So right now we have r. All right, I didn't start solving the problem yet. I'm just like, by the way, I'm just translating the problem. So you are given x as a function of time and y as a function of x. Let's see what is required. Determine the magnitude and direction of the velocity and acceleration when t is equal to 2 seconds. So all what I want I want V, find V and A at t equal to 2 seconds. Yeah. The thing is, you cannot find the velocity and find the acceleration until you find the position, right? Because the thing is, the velocity is the derivative of the position. So how we can do that? If you want the velocity, we just have a rule here. Velocity is the time rate of a change of the position. We just find out what is the position is here. So basically, you are gonna differentiate this position with respect to the time. So you have to differentiate this, dr dt. So you differentiate each component separately. What is the derivative of 8t with respect to t? It's gonna be 8 in the direction of I. What is the derivative of 6.4 t squared with respect to t?
12.8.
12.8 t in the j hat direction. Okay, I found v. How about the acceleration? I'm gonna differentiate the velocity dt, dv dt. The differentiate of 8 is gonna be 0 in the I hat direction. How about 12.8 t is gonna be 12.8 in the j hat direction. So there is no component for the acceleration in the x direction. All the acceleration is going up. Okay, the thing is, I asked you to find them, but the way that I asked about them, I told you to find the magnitude and the direction. That is different. Here I found the velocity vector and the acceleration vector. Can you guys tell me how can I get the magnitude from the vector? Here's the velocity. You have 8 in the x direction and 12.8 in the y direction. So basically your point is here and you move. This is v. This is the absolute. This is you made 8 and you made 12.8. Can you guys tell me what is the v? The absolute value of v? It's a rectangle, Pythagorean theory. So you are gonna get the square root of what? 8 squared plus 12.5 squared. And this is gonna give you an absolute velocity of 26.82. Is it meter or feet? It's feet per second squared. Feet per second, sorry. This is the velocity. Okay, right now I got the magnitude. How can I get the direction? All right. The direction means I want the theta. How can I get theta? You have this and you have that, right? So can you tell me what is tan theta? That's a triangle. This is theta. You have, this is 8, and the opposite is 12.5. So it's gonna be the opposite, 12.5 over 8, right? This is tan theta. So if you wanna find the value of theta, it's gonna be equal to the tan inverse of this quantity, 12.5 over 8, and this is gonna give you an angle of 72.64 degrees. Does anybody have any question? This is basic geometry. So any vector in the world, you have any vector, you can describe it. Like let's say I have x vector, not x, let's say a vector, have 5 in the I hat direction plus 7 in the j hat direction. So this vector has 5 in the x, 7 in the y, and this is the angle theta. This is my vector, which is a vector. You have to go 5 in the x direction, 7 in the y direction. So if you want to find a, which is this value, so it's 5 squared plus 7 squared, square root, you got the value or the magnitude of the vector. If you want to find the angle, tan theta is the opposite, and then tan theta is the value 7 over 5, and then you get tan inverse, and you are done. Okay? Alright, actually the acceleration is way much easier. Can you guys tell me, what is the magnitude of the acceleration? 12.8, because it's 0 squared plus 12.8 squared. Take the square root, you are done. Can you tell me what is the direction of the acceleration? At what degree? What is the angle theta of the acceleration? It's going up. And we measure the angle from the horizontal, so it's gonna be 90 degree, right? If you wanna do it, so you have 0 in the x and you have 12.8 up. So basically, the acceleration A magnitude is equal to 12.8 and the theta is this angle, which is 90 degree. But if you wanna get tan theta is gonna be equal to 12.8 over 0, which is give you theta equal to 90 degree, because this is indefinite, which is the same definition of tan 90 degree. All right? Okay, so right now we solve it an XY problem that has something that is moving in the XY direction. Does anybody have any questions so far? All right. Let me solve another problem.
Professor, you're gonna submit the notes from this class to campus, right?
So really on campus, I did it yesterday.
Okay.
So if you go to Canvas, I put the things by week, so you're gonna find week 1 and week 2. So I put these notes yesterday on week 2, and then once I upload the recording, I'm gonna put it in the same.
Okay,
What number was that example in the book?
Huh?
You said the number of this example in the book was?
This example, 12.9.
Alright, thank you.
The one that I'm gonna solve now, it doesn't have an example number, but I'm gonna put it here. Yeah, the one that I'm gonna solve now is example 12.10. Example 12.10. Alright, so in this example, it says for a short time, the path of the plane is described by y equal to 0.001 x squared. So if you have a plane that is taking off, and this is the x direction, let's say that you are in the airport. Usually the planes doesn't go up like right away, it goes a little bit and then it goes up like this. So that's why the path is something like this. Something like that. Let's say that your plane is here and your plane wanna take off, and this one, y is equal to 0.001 x squared. The more this number is, the more the curve is flat. So this is the path and this is y. Alright, so I give you this and I said if that plane is rising with a constant upward velocity, watch this out, constant velocity. Because once I say constant velocity, what is the value of the acceleration? 0. But by the way, it say upward velocity, that means velocity is in the x and the y direction. Velocity, upward velocity. Here's the wording. If the plane is rising with a constant upward velocity of 10 meters per second, that means that Vy is equal to 10 meters per second and it's constant. So I can say that Ay is equal to 0 because the velocity is 0. Can I say that Vx is equal to 0? No, I can't because I didn't state that. Alright, so I have Vy is equal to 10 meters per second. So, and Ay is 0. Let's say what we have. Okay. Determine the magnitude of the velocity and acceleration of the plane when it reaches an altitude of y equal to 100 meters. So at y equal to 100 meters, so let's say here, y is equal to 100 meters at this point. I don't know what is the value of x. But at y equal 100 meters, try to find the velocity and the acceleration. By the way, I said determine the magnitude. So I didn't ask you about the direction, but to find the magnitude, you have to find the x component and the y component for both the v and a. All right, so let's do this. So I have vy, so right now my mission is to find what is the x direction. By the way, there's two ways to solve this problem. There's a one that is here, I did it a little bit simpler, like if you look here, it's one page. I solved it like in 2 steps, so either ways are fine. So the thing is, I have vy, and I have y as a function of x. So to find v, you need to have 2 components, vx in the I hat and vy in the j hat. I have already the vy, but I don't have the vx. So your mission is to find vx. Vx, we know it is the dx dt. You need to find what is the position in the x direction, is it changing over time? And to find that, you have to do something here. So sometimes we call this So yeah, here's example 12.10. Yeah, it's the same thing, like you will find that the problem here at the end, I solved another problem there about a submarine, so maybe you can practice, might not solve it here, but the problem that we are solving is at page 9 down there. So you'll find it here, solve it in the textbook in a long way. I might do it with the way that I did it here so that we only have 10 minutes, all right? So right now, our mission is to find the Vx. So if you have y is equal to 0.001 x squared, if you want to find the velocity Vy, so Vy is equal to dy dt, right? So I have to differentiate this with respect to dt. Can you guys differentiate this with respect to dt? By the way, this variable is x. What is the derivative of dy dt? This is x, so I'm going to multiply this. This is going to be 0.002 multiplied by x. By here I should put dx dt, because I'm not differentiating with respect to x. I'm differentiating with respect to t. So at the end I have to put dx dt. So let me put it here. I know that Vy is equal to 10 and it's always constant, so I'm going to put it, and then I'm going to put here 0.002 multiplied by x multiplied by dx dt, which is dx. Alright? So that is our versed derivative. If you want to find out the value of Vx at y equal 100 meter, you need to find what is the value of x at 100 meter. The value of x at 100 meter is going to be equal to y divided by 0.001, and all this is going to be under the square root, right? Because this is the equation, you have to put this y is equal to 0.001 x squared. If you have y is equal to 100, you have 0.001, and this is x squared, so the value of x is going to be equal to the square root of 100 over 0.001. And this is going to give you x is equal to, can you guys calculate this one? Because I don't think I did it the same way that I did it here, but it's going to lead us to the same thing. Okay, Vx, actually I'm solving something similar to this. Vx is 15.81, right? I mean like the x value. Alright, x is equal to 316.2 meters. Alright, so that is the value of x. So if you want to find the Vx, you have to substitute with the value of x that we got it here in this equation. Alright, so you're going to have 10 equal to 0.002 multiplied by 316.2 multiplied by Vx. So Vx basically is going to be equal to 10 over 0.002, 316.2, and then you are going to find this value, and the Vx is equal to 15.81, and all these values are in meter per second. Alright, so I found Vx. So if you wanna find the magnitude of V, so it's gonna be equal to Vx squared plus Vy squared, and this is gonna be equal to 15.81 squared plus 10 squared, and this is gonna give you a magnitude of V 18.7 meter per second. Alright, so right now I'm done with the velocity. Let's get the acceleration. So to get the acceleration, you have to differentiate something. By the way, I know here that velocity Ay is constant, so we were able to find out that Ay is equal to 0. So Ay is a done deal. Let's find Ax. To find Ax, you need to find an equation that has Vx and differentiate this equation so that you can generate Ax out of the Vx. So this is the only equation that I have that has Vx. So you are gonna have 10 equal to 0.002 x Vx. Do you guys remember how to do derivatives to a function of two variables? Let's say, I'm gonna do it here very quick. Let's say that you have z equal to xy, and you wanna find dz dt. How we can differentiate it? The derivative of the first multiplied by the second variable plus the derivative of the second multiplied by the first variable. So you are gonna do dx dt multiplied by y, right? And then you're gonna put x and dy dt. Is that right? That's how we do. If it's the three variables, the same thing. The derivative of the first multiplied by the two variables plus the derivative of the second multiplied by the other two, and so on. So same thing here. If I want to find the velocity, I have to differentiate this equation, all the equation, left and right, with respect to dt. Let's differentiate left and right. What is the derivative of 10 with respect to time? Derivative of a constant is going to be 0. Let's differentiate this equation. I'm going to differentiate this part with respect to time, multiplied by this part, and then this part multiplied by this part. So this part is going to be 0.002 dx dt multiplied by dx plus 0.002 x multiplied by dvx dt. What did I do? The derivative of the first part multiplied by the second part plus the first part multiplied by the derivative of the second part. That's what I did. So this is basically is equal to 0.002 dx dt is vx, and you have another vx here, so this is going to be squared, plus this part 0.002 x dvx dt, that is called ax, when you differentiate the velocity in the x direction with respect to time. I have vx, I already got it, and I have x, I already got it. They both are here. So 0 is going to be equal to 0.002 multiplied by vx squared, which is 15.81 all squared, and this is going to be plus 0.002. X is equal to, where did we find it? Yeah, 316.2 multiplied by ax. Now I need to find the value of ax. You're going to send this to the other side, and you will find out that ax is equal to negative 0.791 meter per second squared. So the magnitude of A is going to be equal to the square root of ax squared plus ay squared, and this is going to give you 0.791 meter per second squared. And definitely the magnitude is positive because you are taking the square root of the square of the negative value, which is going to be positive. Does anybody have any question on that? So what did I do? You have an equation y is equal to x squared, and you have another equation that gives you v1. All right? So all what I did, I take the derivative of this equation. One time, it gave me vy and vx. Another time, it gave me ay and ax. I was fortunate enough that he gave me the velocity in vy And he told me it's constant, so I also know the acceleration in AY. And once I know these two quantities, I will end up with one equation in one variable, which is dx, and another equation in another variable, which is ax. So when you are given a displacement, you differentiate one, you get the velocity, you differentiate another one to get the acceleration. Alright, see you guys next time. And watch out for the video that I'm gonna upload, and I also uploaded the notes on campus.